Good afternoon. Welcome to this session on HPC numerical methods. There are 3 papers being presented in this session. The first one is being presented live, and the remaining 2 are pre-recorded videos. But the speakers will be available to answer questions for the pre-recorded videos. The first paper is being presented by William Moses, and he's presenting a work that is a collaboration between MIT, Argonne National Laboratory, and Technical University Munich. So, yours.
Thank you so much. There we go. I will be presenting our paper, Reverse Mode Automatic Differentiation and Optimization of GPU Kernels via Enzyme. So, as mentioned, this is a large collaborative work, not just me on it. So, to begin, I thought we'd start by talking about everyone's favorite subject, AP calculus. So, as a quick refresher, derivatives are this nice utility that will tell you the rate of change of a function's output given a function's input. Now, this has a wide use of applications inside of the sciences. Specifically, inside of machine learning, you might know this as backpropagation within neural networks, or inside of scientific computing, you might see this in any sorts of physics simulations or differential equations for modeling. What's really cool is it turns out you can ask a computer to automatically compute these derivatives for you. So for instance, suppose we have the definition of this ReLU3 function on the left. We can use a tool to automatically generate the corresponding gradient for this code shown on the right. And unlike numerical approaches where you say, give it a function at one point and a function at a nearby point, this doesn't end up having any approximation error. And moreover, it can also compute the derivative of either all of the inputs or all of the outputs with a single call. Existing approaches for doing this automatic differentiation tend to lie in one of 3 different categories. The first of which is called using a differentiable domain-specific language, or DSL. In essence, the tool builder has written a new language which was explicitly designed to be differentiated. To use this in practice, it requires taking your existing code, such as this ReLU3 function on the left, and rewriting it to be written in all of the specific primitives provided by the DSL. Now, this works out really nicely if that DSL supports all the operations that you care about and, moreover, has primitives that closely match exactly what you're doing. But if this isn't the case, it may be quite hard or sometimes even impossible to represent it. The second approach is known as operator overloading. Tools that follow this are known as, say, either adept inside of C++ or JAX inside of Python. In essence, rather than having an entirely new language, you say, I'm going to make differentiable versions of specific language constructs. So inside of C++, instead of having the regular double type for storing floating point data, we'd have this special differentiable A double type. Or if we want to use Python and JAX, instead of calling a numpy.sum or np.sum, I'm going to instead call now a jax.sum, which does a similar sort of utility. And inside of those special versions of the operators, it'll make sure to go ahead and store all the information that's required to perform the computation of the derivative. Now, of course, these special operator overloading tools may not exactly match all of the types of programs that you have originally. For instance, JAX doesn't necessarily support all of the linear algebra within NumPy, so you still may need to do some rewriting. However, the much bigger problem here that tends to occur in practice is that these tools store the individual instructions that are executed and then later interpret those instructions, which can be quite slow in practice. The third approach is known as source rewriting. In essence, I have a tool that takes the source code of our entire program or entire application, and it'll generate new source code that computes that derivative directly. So at the bottom here, I have this cool tool called Toponod that takes in some C files, some header files, and all together creates new versions of these C files and header files which compute the derivative. This can be quite efficient in practice since it looks exactly like you'd write it by hand. However, it also comes at a burden because this tool has to re-implement the parsing and semantics of that given language. So if you have a new language feature or something else new that comes up, then the tool may not be able to handle it. Moreover, because it requires all of the code that you may want to differentiate to be available to thus produce the differentiable version of it, it makes it rather hard to use it with external libraries. Generally, all of these 3 approaches tend to follow the same pipeline. First, I have a program in my favorite language. Then I run it through an AD tool specific to that language, which generates me new source code once again in that very same language. I then undergo the traditional compiler optimization pipeline, which in this case involves going to LLVM, running some optimizations, and finally ending up with the executable that we decide to go ahead and run. Let's see how this works in practice on a little sample code I have here. So I have this normalize function, which will give in two vectors, set as the output vector the normalized version of the input vector. And for every index inside of that array, I'll divide by the corresponding magnitude of that input vector. Since the magnitude operation itself takes O of n time to run, code in this form takes O of n squared time to compute the total normalize function. Now, any good compiler worth its salt will realize that that's not the most efficient way to write the code, and I can instead hoist the call to the magnitude function outside the loop, reducing the runtime from O of n squared down to O of n. Now, if we were then going to go ahead and differentiate that optimized program, the way the algorithm works is to effectively run all of the instructions in your original program, except now in reverse, to compute the corresponding derivative. So if we had that magnitude outside the loop and then a for loop, the corresponding derivative would do the for loop in reverse order, followed by the gradient magnitude function. However, that's not how those existing tools work in practice. Those existing tools have to operate at the source level. So they first have to apply automatic differentiation before they can do any of these optimizations. So here we have that unoptimized version of the code with magnitude inside the loop. We then run automatic differentiation, which gives us a gradient code with, again, now magnitude still inside the loop. But when we go ahead and do our optimization after the fact, we're not able to get that faster version of the code because the call to the gradient magnitude function uses a variable defined within the loop, leaving us with the slower runtime. In other words, if we're able to push differentiation after optimization, we can end up with asymptotically faster gradients. And this was explored in an earlier paper presented at NeurIPS using a tool called Enzyme, which implemented automatic differentiation inside the compiler or inside LLVM. So this allows us to first take in any of these input codes, not even now have a separate tool per code, but whatever your input is, then run optimization, then automatic differentiation, and we can do some extra optimization after the fact. And by pushing that down to the low level, we can get that goal of being able to work on optimized code. And in that paper, it demonstrated the ability to get a 4.2x speed up over existing approaches that had to do this the other way. Also in that paper, it enabled the ability to import arbitrary foreign code into a machine learning framework like TensorFlow by packaging up Enzyme for use inside of either TensorFlow or PyTorch. Let's now get into a little bit of the meat of this tool. So specifically, it's built on top of a compiler framework known as LLVM. What's really interesting about it is it's used for almost every language in that it has the ability to lower from that source code into this intermediate representation. You can think of it somewhat as a cross-platform assembly. In addition to having many different types of inputs, it also has many different types of outputs. It can go down to CPU code, to GPU code, whatever your architecture is. And moreover, it has a well-defined set of both optimization passes and analyses. Now, prior work, including the prior work on Enzyme, has not been able to explore reverse mode automatic differentiation of GPU kernels. In fact, no one has been able to do that for existing GPU kernels. And the reason for this is one of three different pieces. The first of which is that reversing any parallel control flow, not even specific to the GPU, can quickly lead to incorrect results. The second problem is that the complex memory hierarchy and performance characteristic of the GPU make it difficult to create efficient code that runs on the GPU if you're just going to write GPU code. And the final reason is the GPU has very specific limitations in terms of the memory that can prevent the entire function from running at all. What we were able to do by solving all of these problems simultaneously is to be able to now perform reverse mode AD of generic GPU code for the first time. So let's talk about those three unique challenges. So let's say I have this source code here on the left of a parallel for loop. What it does is for every index of this array, sets the output of that index to be the same input value. In essence, you have a read race in that all threads read the same memory location. Unfortunately, this reversal process in the algorithm turns writes into reads and turns reads into writes. So whereas beforehand we had this perfectly safe simultaneous read across all threads, now when the reverse or the gradient pass, we have a simultaneous write across all threads, which quickly can lead to incorrect results. The second problem that I mentioned earlier is the complex structure of the GPU memory hierarchy. So at a broad overview, there's three types of memory that people tend to care about. The first of which are registers, and there tends to exist a uniqueness of the register per thread. There's only order of bytes of these across the GPU, and moreover, if you use too many registers, you're not allowed to run as many things in parallel. However, they're also the fastest possible primitive you can use. So whenever you want, and you don't use too many of these, you want to put everything in registers. A little bit slower, the GPU has also something called share memory, which is used across a block, and it has on the order of kilobytes. Now, again, if you use too much of these, it limits the number of things that you can run in parallel. It's a little bit slower than the registers, but it's still quite fast to use in practice. And finally, you have global memory. So if you see NVIDIA advertising, oh, this has 24 gigs of RAM, that usually means that there's 24 gigabytes of global memory. Now, there's a whole lot more of it, but it's intensely slow. So in practice, people tend to see when they first write an application that the performance is limited by how many reads and writes to global memory that they have. So the way that we solve both the race problem and the memory hierarchy problem is to come up with a different way to resolve races depending on which type of memory you're using in the first place. So specifically, if we're able to have a fast version of the race resolution for the very fast input type of memory, such as a register, and similarly, we're allowed to still have a relatively slow, by comparison, way of updating the global memory, and since that was already slow to begin with, we maintain roughly the same performance characteristics as we had in our original code. So if we had those thread local memory locations, such as registers, we can just fall back to a non-atomic load and store, since there is no race. If we have the same location across multiple threads, as may exist with shared memory, you can do a parallel reduction, and that's quite efficient. And finally, if you don't know anything else about what's going on, for instance, as may be the case in various types of accesses to global memory, we can always just fall back to an atomic increment. The next bit that needed to be fixed is the GPU has specific characteristics for saying that some code must complete before another piece of code executes. Specifically on the GPU, we have this notion of async threads. So if we have first this code A, then the sync threads, then this code B, then we have the guarantee that all of the threads have finished executing code A before they're allowed to execute code B. And we produce the corresponding reverse of this synchronization instruction by putting a synchronization at the corresponding place in the reverse pass. And then we prove correctness of this algorithm by going through the different types of cases that can arise. One example of these types of cases is suppose that the first piece of code stored into a particular location, then we synchronized, then we loaded in the subsequent code. And the corresponding gradient for this would be an atomic add, as we saw earlier, into the shadow or the gradient value of that pointer location. Then we'd perform a sync, and then we would load that value to propagate it to wherever it was used by. Now, because the sync occurs after the atomic adds have completed and before the subsequent use, we're guaranteed that that load at the end has seen all of the values that have been added into it, thus ensuring correctness. If we were now to take this on a fully fledged, but relatively small, so I can put it on the slide, CUDA example, we have this code first here on the left, which is a device function for running on the GPU inner, which says y of thread index equals a times x of thread index. We can, below here, call this magic intrinsic function enzyme autodiff, with as the first argument the function we want to go ahead and differentiate, with the corresponding both original arguments and shadow arguments, which is where we're going to put our gradient results into. Now on the right, we have a rough translation of what this gradient would look like. Of course, we operate at the LLVM level, so we don't actually generate source code like this, and thus this is a higher level representation of the code that actually exists. So first we again run that original code, then we run the corresponding gradients of all those instructions in the forward pass. So first we do the gradient of the store, then we propagate to the two operands, first into x and next into a, what the corresponding gradients of x and a would be. Now first we see here the atomic updates, because we're saying suppose we didn't do any analysis to prove that it was either thread local or the same memory location. But as mentioned before, we can do these analyses on the memory locations and then optimize the first atomic into simply a regular load and store, since it's a thread local address. And the second place was the same memory location, so we can do a reduction across all the threads. Now, this doesn't just work on, say, C or C++ code, but because we operate at the LLVM level, we can take GPU code both in a variety of languages and a variety of architectures. So here I have Julia code for both CUDA and AMD GPUs that say start by creating some shared memory, and then eventually we say go and compute the gradient or derivatives of these. And if this is of interest to you, we have the full source code examples listed at the link below. Now, that's almost sufficient to get us GPU differentiation. The one little issue that still comes up is suppose we take a look at this code snippet here on the right. I say the output equals x squared. Then I set that variable x to equal 0. I know that the derivative of x squared, right, is 2 times x. But I've already overwritten the value of x to be 0. So there's no value x for me to compute that 2 times x in the derivative. So what we actually have to do is if any of this memory is needed to compute the reverse pass, and also potentially overwritten, we need to do something to preserve it for that reverse pass. So here, as an example, I allocate a new cache. I store that value before it's overwritten. Then I can use that cached version. Now, this gets us correct code, but it's no longer terribly efficient, specifically because the more memory you allocate and use on the GPU, the slower your program runs. And moreover, if you allocate and use too much memory, it may not even fit on the GPU anymore. Like in that original NERVS paper, being able to apply optimizations first helps this overhead. However, now on the GPU with this complex memory hierarchy, it's no longer sufficient. So we remedy this by introducing novel, both automatic differentiation-specific optimizations and generic GPU-specific optimizations. And that's able to speed up the program by several orders of magnitude, and thus get a relatively good runtime at the end of the day. So let's go through a couple examples of these. So first here, I'm using 2 variables, x and y. I'm summing them up, then I'm calling sum function with it. When I want to compute the gradient of that use function of sum, I need that original sum of x and y. However, I don't actually need x and y individually. A naive strategy for performing this cache is to say, OK, both x and y are overwritten, and I may need them in the reverse pass. I'm just going to cache x and y. However, if we look at the data flow graph here, we notice that we can, instead of choosing x and y, just cache the single variable sum, which will save us half the memory, since there's only 1 location to store, rather than the 2 locations of x and y. Generalizing slightly for an arbitrary graph, what we do is we run a minimum cut over the total graph that separates the variables that are potentially overwritten from the ones that are actually required. Another example optimization that's not even specific to differentiation is we may be allocating a lot of these caches potentially. So suppose I have 2 allocations, var1 and var2. And I notice that they're in the same scope. It turns out that any calls, especially allocation calls, are very expensive on the GPU. So rather than having these 2 separate allocations, I'm going to fuse them into a single allocation and have the second variable just be an offset into that first allocation. And that, again, works not just for this use case, but any program that runs on the GPU can take advantage of this optimization. We wrote a wide variety of these different optimizations, some of which are specific to the subject here of differentiation, and some of which are just specific to any code for the GPU. And if you're interested, there's a more in-depth list and description in our paper. We then took this, and we took 6 different large HPC benchmarks and saw how it worked in practice. So let me set this up for you. What's plotted here is the relative overhead. So first you run the original forward pass code, which computes the original outputs. And you also simultaneously compute the derivative of all of the inputs, for which there can be millions of parameters, so it could take a very long time. Now, in practice here, if we see that Lulesh, for example, has an overhead of 2.01, that means in 2 calls to the original function, I can get both the original outputs and the derivatives of all of the inputs. So these all tend to be relatively fast, within an order of magnitude of the original program, with, of course, the exception of this DG code for CUDA. And this code we happen to run on both CUDA and AMD devices, and we found that the reason there's a relatively large overhead for that one is actually that CUDA has a bug in the register allocator. So if you happen to run it on an AMD GPU, you're OK. Diving in a little bit deeper in case any of these benchmarks are known or interesting to you, the first 2 are 2 different Julia implementations of a discontinuous Galerkin kernel. The next one is a lattice-Boltzmann method. Next, we have the Livermore's unstructured hydrodynamic solver Lulesh. And finally, we have both a memory-bound and a compute-bound version of the DOE proxy applications XSBench and RSBench. Let's now see how well those new optimizations we talked about earlier actually work in practice. So first, suppose I apply no optimizations. I just differentiate the original codes in their full form. It turns out that 5 out of 6 of these benchmarks instantly run out of memory, making them unable to run. In the 6th one, it still works, but it runs 3,000 times slower than the original function. Technically functional, but not necessarily good. We then go ahead and run those pre-processing optimizations. So recall earlier in that NERVS paper, we talked that by working at the lower LLVM level, you're able to first apply optimization, then differentiation. So this blue line here represents just first applying optimization. And that makes most of these programs now run, though there's still a couple that aren't able to run. And it reduces the overhead. You have, like 1,300x for DG on CUDA, 6,000x for RSBench, and say 26x for XSBench. So it runs. It's OK, but not great. Then in green, we apply all of those novel both GPU and differentiation-specific optimizations we talked about earlier, which brings us down to that relatively efficient runtime within an order of magnitude. And the real takeaway from this slide here is to say that in order to get tractable performance, let alone the ability to run this at all, you really need to integrate optimization into the differentiation process when you're running on the GPU. Overall, Enzyme is itself a tool for being able to perform reverse mode automatic differentiation of any statically analyzable LLVM-IR. This enables it to differentiate code in a variety of languages, be it C, Julia, Rust, Fortran. Here we present now the first general purpose reverse mode automatic differentiation for the GPU. And we're able to achieve that by first resolving all of those races, but 2, introducing those novel GPU and AD-specific optimizations. By operating also at this low level, we're able to not only have this work for a specific vendor, but it works on AMD and NVIDIA GPUs. The code is open source. We have documentation and more on our website, and the full code is available on GitHub. If you're interested in using this, we have weekly meetings on currently Mondays if you want to talk more in depth. We also have ongoing work to support both CPU parallelism, such as OpenMP and MPI, as well as both forward and mixed mode differentiation. There's a whole host of people who contributed at some part to this work, be it helping test out codes, having bug fixes, or looking over early drafts of this. Specifically here, there's also a number of funding agencies that we'd like to thank. I was personally supported primarily by a fellowship from the Department of Energy, and several others were supported by both DARPA, the German Research Council, as well as various national labs and the US Air Force. Thank you so much. Any questions?
Yes, you have questions. I will speak them out for you.
Sure.
So, the first one is, you mentioned external libraries are typically not supported by AD tools. How are external libraries whose code is not represented in LLVM-IR supported?
Sure. So we have 2 different ways to being able to support external libraries. First of all, if you happen to compile that library itself with a flag known as either link time optimization or embedded bitcode, we're able to run the differentiation process at link time when you have to have all these code components available. In addition to that, we also support what are referred to as custom derivatives. So if you, a vendor, wrote some custom assembly code or whatnot, you can say that the derivative of this custom foreign function is this other function, and thus we can still differentiate through any code that calls it.
Next question, what happens when the code Enzyme is trying to differentiate is not differentiable if statement or absolute value or the derivative is multi-valued?
Sure. So we can differentiate through control flow, such as an if statement or a for statement, perfectly fine. The algorithm for doing so is effectively to branch to whatever your predecessor was. So if you have an if statement going to 2 blocks and then merging between, the derivative of that merge point is to go to wherever you came from. If you have various types of multi-valued functions, what we do is we choose the specific path, which is equivalent to the path that you came from your original code. So for example, if you wrote something that computes the max of an array of numbers, in implementation, it would look like I'm picking the last max, or say the first max. And what Enzyme would do is get you the specific implementation derivative. So if you're picking the last equivalent max, we would set a 1 to that last equivalent gradient value.
Next one, how is dynamic control flow supported? An example would be data-dependent while loop.
Sure. So if you have dynamic control flow such as that while loop, an example would be you're iterating through a linked list, for instance. We would similarly perform the corresponding branch to the predecessor that you came from. This could still involve saying, OK, did I exit the loop at this point, or am I going backwards in time, which may involve some of those cached variables we talked about earlier. But regardless, the data dependency or other types of dynamism are resolvable by just ensuring you go back to the corresponding predecessor that you came from.
Next one, is there any downside of operating in the LLVM IR rather than the source code? I'm wondering if some optimizations would not be possible from LLVM IR.
Sure. So there's a couple of different things that you may want to achieve. So one of the problems that the original Enzyme paper resolved is that when you get down to the LLVM level, you may not have all the full type information. And Enzyme resolves this by introducing a new interprocedural type analysis that detects the corresponding types of variables. There are still, however, some high-level operations that you yourself might know. For instance, if I'm taking the derivative of some function of a unitary matrix, I, from high-level linear algebra, might know that that's 0, whereas this would still go instruction by instruction. This is similarly resolvable by introducing your domain-specific information as a custom derivative. So you could say, oh, if you have a function which is compute some particular thing of that unitary matrix, I could just say always immediately return 0, rather than using the automatically synthesized version.
Next one, is forward AD of those benchmarks expected to blow up memory or something else on GPU?
Forward mode differentiation, depending on how you do it, tends to use less memory. The reason for this is that rather than having it first run the parameters forward and then run them in reverse, you have immediately all of the variables as they were defined available since you're just running it forward once. The difference, however, between forward mode and reverse mode is that forward mode takes one input and then correspondingly goes to all of its outputs, whereas what reverse mode does is in a single call give you the derivative of all inputs with respect to a single output. So then that means using reverse mode, you can get the entire gradient as once, whereas forward mode requires you to do an individual call. Of course, each of those calls may use less memory, so it's a trade-off depending on your use case.
So this is the last question that I'm speaking out here. There are a few questions, but we are running out of time, and so I assume that you will answer them in the Slido chat, right? Yeah. So the last question here that I'm bringing out is, are there any plans to build Enzyme on LLVM MLIR, if that's not what you're already doing?
There are indeed some in-progress plans and partial implementations for doing MLAR. Specifically, we have some ideas that might be interesting to combine that with scheduling. If you're interested in that, feel free to talk to me at length about that offline. Thanks.
Thank you.